Right, good morning to everyone in Teams. Good morning. All right, good morning, good morning, good morning, good morning. Good morning to everyone at Microsoft Teams.
Good morning, Dr. Cooper.
Good morning.
I have a concern.
Yep. Go ahead. Actually, I'm on the recording. Can we wait to offer its recording, or if it's fine, you can sit over the recording. But if you want to, we can wait until I end the recording.
Oh, it's fine. I was going to say the homework on mastering chemistry is really hard, and then on I can't think. Wait, it's chapter 7. Some of that stuff we haven't been over.
Yeah, that's right. That's right. Hang in there. We're trying to get there. Just hang in there.
Okay.
It'll make sense soon. I promise you. Okay, I'm gonna wait another minute or so just because I gotta admit a good group of students. And today we want to talk about the carbon cation rearrangements. All right, there's 4 potential ways that we can rearrange carbon cations. All right, we'll talk about the reason why these are going to occur, and then hopefully I can go back and try to address some older questions that came up. If not, I have to do it on Friday. But I want to make sure that I cover this today. All right, so give me a few minutes here to keep letting students in, and we'll get started. And again, good morning to everyone on Microsoft Teams. All right, I'll wait 1 minute, and then I'll get started. Good morning again to everyone in Teams.
Good morning, Doc.
Good morning, good morning, good morning. Okay, I'm going to go ahead and get started. I'm going to try my best to manage those that are needing to come in class. You guys will tell me if people are trying to message me that I'm not able to see any messages. All right, today lecture is focused entirely on carbon cation rearrangements. All right. So let's kind of first of all think about what am I trying to say here, right? So the whole idea is that if I started off with this type of carbon cation, you guys would tell me this would be what type? Classification type.
Hey.
Primary carbon cation. All right, and a primary carbon cation for the most part is not stable, right? So let me change the settings here. Okay. So if possible, we would love to potentially go from something that's primary to something that's a little bit more stable. Let me do this. Okay, what's going on here? So this primary carbon cation, if it could, would love to move to this version of itself. And you will call this version on the left what type of carbon cation? Yeah. Must be a tertiary carbon cation, right? All right, so that's the whole idea around carbon cation rearrangements. All right, this is an aerial. Let's change that. All right, is that carbon cations would prefer, this is the least stable form of this compound. And really quickly, can anybody tell me why the primary carbon cation is least or not as stable versus the
because it's only connected to one carbon.
okay. Can you break that down a little bit more? What is that being connected to one carbon do?
The car it has more electrons to share with versus only sharing with three hydrogens and one carbon. It has two carbons it can share electrons with now.
Okay, that's exactly right. So primary carbon cations are not substituted as much. And what I mean by substituted, they don't have a lot of neighboring carbons. And not having a lot of neighboring carbons are going to destabilize you because I don't have the stabilizing effects of having carbons. Right? Carbons are electron withdrawing, electron releasing or electron donating. So they're going to stabilize any species that needs electrons. And a carbon with a plus is indicating a carbon that needs electrons. All right, so I'm going to put this here as a main principle of rearrangements is that I want to stabilize myself, okay? So any way I can stabilize the carbon cation, the better I would be. Stabilize. Is it L in there? It's an I. That's misspelled. Okay. If I can stabilize myself, I'll be better off. All right, is everybody kind of comfortable with that principle? Let's go into the ways that we can do this because my time is, I'm feeling it's going to be up just on simple stuff. All right. The first way is a hydride shift. All right. And this is typically one of the most common ways to stabilize. All right. So a hydride will move to generate a more stable carbon cation. Take a look at the hydride shift really quickly. All right, I'm going to start off with this alkyl halide. I'm going to introduce it to, I'm going to use the same nucleophile that I always use, a carbon nucleophile. All right, we haven't talked about the names of this yet, but this is a lithium acetylide. We'll talk about those soon. I got this compound, and I'm going to use a solvent here as methanol. Okay, so if I have methanol, this nucleophile, and this alkyl halide, what will you guys tell me about the mechanism type that I'm favoring here? What will you tell me? This is favoring what type of mechanism? All right, hopefully you guys are saying SN1 in your mind, right? How do I know that? My alkyl halide is secondary, right? So secondary is free to do SN1 or SN2, so I need more information. My nucleophile is strong, right? However, we said that the solvent is a big contributor because it's in large quantities. And my solvent here is polar aprotic. This is going to have nitrogen bonding effects, right? So this is going to really facilitate this leaving group leaving first or compose or opposed to the nucleophile attacking while the leaving group leaves, right? So this is going to favor the SN1 mechanism. So the first step of this mechanism is going to be where my leaving group just leaves, right? Right, and everyone hopefully is comfortable with drawing the intermediate that comes from that step. You should generate this intermediate here, right? And if you have to classify this carbon cation, what would you tell me it would be?
Secondary.
This is, yep, this is a plain old secondary carbon cation. All right. And I always told you guys beforehand is to beware of rearrangements. All right. In this case here, there are neighboring hydrides. All right. This is the first of me teaching this online like this. All right. So I'm trying to I can. So let's go ahead and color this red. To the right, I have a hydrogen. And also to the left, there's a potential hydrogen, right? So we said the first way that carbon cations like to rearrange is through a hydride shift, all right? So let's go ahead and do both potential shifts to kind of make it point here. This will be a teaching moment here. If I did the hydride shift from my right-hand side, let's see what happens, all right? And again, you guys know what a hydride means, all right? Keep this in the back of your mind. Hydride is a hydrogen with 2 electrons. So the hydrogen with 1 electron is called hydrogen, and hydrogen with no electrons is called a proton, and the hydrogen with 2 electrons is known as a hydride, right? There should be a negative charge on that. Okay. So this is what the hydride looks like. IDE for like a compound that has a negative charge. All right, so that means when I do the mechanism, I'm really describing the movement of an H with its 2 electrons. All right, that's why we use the word hydride. So I'm saying this hydrogen with its 2 electrons, we're going to want to move to the carbon cation. Okay. So when we do that, I'm going to draw that fresh. I'm going to generate now this compound. Right? I'm not going to draw the other H here. It's understood to be there. I'm just going to do the first hydride shift. I'll draw one of the H's here. Right? And you guys want to keep in mind that there was already an H there, and I'm going to color that gray. Right? I'll color this one in red. That's the one that moved from the hydride shift. So I went from a secondary carbon cation to a what when I did the red hydride shift? What type of?
Primary.
Yep, that's a primary carbon cation. Is that favorable?
No.
Oh,
Very good. All right. So this is where what you guys want to do mentally when you're thinking about all the potential rearrangements. You want to make sure that it goes in a correct way. All right. This is not productive. Right. So that means that this does not occur. It's not favorable to go from a primary to a secondary carbon cation. I'm going to color that in gray. All right, what happens if I went for the hydrogen that's on my left-hand side? I just need a better color. I don't like that color inside. All right, so how do I draw that mechanism out? All right. So again, we say that we're moving a hydride. And what's a hydride again?
When it has 2 hydrogens.
Yeah, the hydrogen atom with its 2 electrons. That's right. Very good. So I'm going to start at the line here, right? That line is saying the electrons. And I'm saying these electrons are moving next door now. Let's put that in red. All right. So when I draw that molecule out, what do I get now?
get a plus.
So I still added a plus to the original carbon. I'm going to call this purple now. But my plus is not on that carbon, is on this carbon, right? Because this carbon lost an electron in 2 electrons in the H, right? Now those 2 electrons just moved over. So what type of carbon cation is this? Can anyone help me out here?
Would it be a tertiary?
Yeah, this is a tertiary carbon.
Why is your arrow pointing to the left then? I mean to the right. Why is it pointing to the left on the top?
Why is it pointing to the left or to the right? Not too sure.
On the middle figure, why is the pink carbon arrow pointed to the right and not up?
Pointing to the right and not up. Not too sure what you're saying.
Because you're moving the plus sign
Yeah, okay,
to the
good.
carbon in the middle.
Good. That's a common error that students make. And so the way that you kind of work out of that idea is to think about this. Electrons do the work, not positive charges, right? So these arrows are not showing where the positive charge is moving. Indirectly, the positive charge is moving, but it's showing the work of electrons. So the hydride, the 2 electrons in this bond to H have to pop over here. A consequence of losing 2 electrons, you gain a what charge? A formal plus charge, right? So the way that you show that is that you have to show the electrons in this bond to hydrogen moving over to this carbon that has a plus. Indirectly, this carbon now becomes plus. Right? Does that answer your question? The same thing that happened here, these 2 electrons move from this carbon over here. So now this carbon has 2 electrons in the H, no formal charge, but because I lost 2 electrons, I gained away a formal plus charge. So arrows always show the work of electrons, right? If you want to think about that, electrons do all the work. Good. So now I have this carbon cation, and this carbon cation will be called a tertiary carbon cation. Is this a productive move?
Yes.
It is, right? Okay.
So will we go with that one?
Yep. This is the correct shift here.
So that's the intermediate that we need to draw.
Yep. So you want to make sure that you see this rearrangement because the final product will change because of the fact it went through a carbon cation rearrangement.
Okay, on the initial one, like the middle one, how did you know to put the H's there?
They're already understood from LIGO structures, right? So this carbon has only one line drawn, so the potential H's. So maybe I should
So
draw
why you only draw one?
because only one hydride shift can occur.
Okay, so long as you know, well, okay, so long as you know it's the H supposed to be there, you draw one H.
That's correct.
So why you didn't draw H on the other end?
On which end?
What'd you say?
I didn't hear you. On which end? I'm sorry.
On the left end, on the same line angle, but H is on the other end. No, still the middle, but the far left.
Left. Yeah,
Over.
there's 3 H's there. I don't.
No, that's it.
And there's an H here in the middle. Far left, this molecule.
But I'm saying, why didn't you put one on the end?
Why?
Because it's one line, meaning it's 3 hydrogens.
Yep, there's 3 hydrogen understood here. That's right.
No, Dr. Cooper. On the other end. No, still the middle. Left.
Right here.
Keep going, keep going. Yes.
Right here.
Yes, sir.
Because it's already understood to be there.
So it's understood on the other end too.
That's correct.
But you drew a H.
I'm drawing them because you asking me to. I'm not too sure I follow what you're saying. So let me erase.
Okay.
Let me
Like,
say it like this. I think I understand what you're trying to say. To show a mechanism, you have to show what's moving. And because I'm doing a high drive shift, I have to now draw in what? One understood H. I don't have to draw all the potential H's here, but to do the mechanism, you have to draw an H. There's no way I can show a high drive shift without drawing a line to an H. Does that make sense what I'm trying to say?
Yes, I get that. But I'm saying on the other end, why didn't you draw one H?
On this end right here, so the only high drive, one carbon away from the plus.
Okay.
Any other, these high drives are too far to do a high drive shift.
Okay, gotcha.
Good, good. Any other questions? Good questions, I guess. I didn't understand it, but thank you for helping.
I got a question.
Go ahead.
How do we know when we have to use the high drive shield? Do we use it?
Yep, you have to train yourself to always think of possibilities. I think that's the beauty of, to me, of organic chemistry, but I know that's one of the difficult parts that students don't like. There's no real formula to organic. So for me, I like that because it gives me an opportunity to be creative, but it's something that you just have to train yourself to think in the back of your mind. So today we're going over all the potential possibilities for rearrangements. And then you'll just train yourself to think about that happening. Are there neighboring protons? Is there a potential for resonance? Is there a potential ring? Is there potential methyl groups? Things of that. You want to think along those lines to kind of see about all the potential rearrangements. I'm going to try to help the best I can to get you guys to try to train yourself to think about rearrangements happening. But yes, that's a very good question that you're thinking about. And that's the question you should be thinking. How do I prepare myself to be able to do these type of things for products? And it comes from just training and practice.
Okay.
Okay, good. Any other questions that come up?
So whenever you're drawing the mechanism, you showed like the one that's productive and the one that's not productive. Do you have to like
No,
draw each one separately?
No, good question. Very good question. No, you do not need to show the unproductive way. I'm doing this for teaching purposes.
Okay, so you would just draw, like, if you're doing the productive one, just one arrow, or
Yep.
do you still do?
Yep, you would just draw the one in red.
Okay, thank you.
Yep, no problem. I'm gonna try to get to some ones that we're due where I don't have to try to do a teaching moment. But I'm trying to do it this way just to showcase why I did the high drive shift with that hydrogen and not any other hydrogen. All right, and another good question came up that I didn't say out directly is that you only can choose a neighboring carbon's hydrogens. All right, you cannot go too far. All right, just next door, one over is all you can go. Okay, and only one rearrangement happens. Right, so once you do the rearrangement, that's it. Now keep in mind, high drives are pretty small, so these things move. But once they move one time, the nucleophile is already looking to attack. All right, so there's not a lot of time for second rearrangements to occur. All right, I'm going to put this down here for what a high drive means. Okay, good. So what's end up happening in this mechanism, let's go ahead and do this, is that now I'm going to generate this carbon cation. Right, and we know that this happens through a high drive shift. Then my nucleophile is going to attack, right? So now this is ready to attack. Actually, I'm not going to show the nucleophile attacking. You guys can let's follow that with your mind. And that's going to give me my new product. Sorry, I can't get my mouse to work correctly here. That looks like this. All right, just wanted to, yeah, it's like a cleanup. Need better than that. Okay. So for right now, I know there could be some potential questions, and there's some things that have to come through a little bit of practice here. But hopefully, you will see here is that initially my leaving group was on the second carbon from the end, and under normal circumstances, the nucleophile would attack this carbon. Because there's a potential rearrangement now, I do a hydride shift to where now I get a carbon cation here, and the nucleophile now attacks at this carbon. All right. Here's your potential question here. Why don't I draw a wedge in the dash? We established last class that anytime that I attack a carbon cation, I should get both a racemic mixture, right? I should get both the wedge and the dash. Why didn't I draw that here for this molecule?
Does that have something to do with the double or the triple bond?
Not really. Not really.
Does it have to do with the shift?
The shift did this indirectly.
So you already addressed the racemic part by doing hydride shift?
Not necessarily. A carbon cation rearrangement could lead to a racemic mixture. I'll give you guys a second to think about it. I'm going to go ahead and try to redraw this out. Any other takers?
Can you ask the question one more time?
The question is, why don't I draw a wedge and a dash indicating a racemic mixture?
You said indicating a racemic mixture?
That's correct. So whenever you attack a carbon cation, right, you guys want to make sure you got this down conceptually, that you can always potentially attack from the top and the bottom, right? That needs to be a carbon cation that's flat, sp2 hybridized. I'm triggering a planar. So why didn't I draw that here?
Because it's not sp2 hybridized.
Okay, most chiral centers not going to be sp2, so you can always draw a wedge and a dash potentially. All right, the reason why is that that center that has a nucleophile is achiral. What does that mean to be achiral?
It has repeating groups.
Yep, not chiral. That's right. So in this case here, because I put a plus on a carbon that has two methyl groups already, I can't draw a wedge and dash. Right? If I see that on a quiz and on an exam, I'm going to take out points. I'm going to say, hey, that chiral, this center is not chiral. So drawing a wedge there or drawing a dash there doesn't make any sense, right? It's not a chiral. So keep that in mind. If your carbon is not chiral, you don't have to draw the wedge and the dash. Line is fine. Okay. That was a slightly tricky question, but not super quick. All right. Let's review really quickly what happens here. All right, I think everybody's comfortable with the fact that my leaving group leaves. I'll generate this carbon cation. I do a hydride shift to form a tertiary carbon cation. And now my nucleophile attacks that center to generate this compound. All right. Let's move on to the second type of rearrangement. All right.
Dr. Cooper,
Go ahead.
when we draw the final product that it give us, is it a certain type of way that we like? Do we have to draw it like that?
No, it doesn't have to be drawn. You just want to make sure you have the correct bonds, right? This carbon here should be attached to the carbon that has that came from the carbon cation.
Right.
So this is the bond, but as long as all the atoms are drawn correctly, you're fine.
Okay.
Okay, the next type of shift, methyl shift, all right? Now a methyl group will move to generate a stable say more stable carbon cation. All right, let's take a look at an example of that. All right, I'm going to have this compound.
Dr. Cooper,
Go ahead.
just to prepare myself, will there ever be a time where we'll have to do a hydride shift, a methyl shift, and all the other shifts in one problem?
Nope. Good question. No, it will only be one of the 4 potential ones. Good question. All right, I'm going to use the same nucleophile. I don't know why I just wanted to use this. I'm going to use one of the most complicated ones possible. All right, and I have this substrate. Let me give myself here in the document settings. Okay, let's see what happens here. So again, I want to make sure everybody's comfortable with this. This is going to be an SN1 mechanism. Everybody tell me why this is SN1?
Because you have the polar protic solvent and the strong nucleophile.
Yep. So polar protic is really the key here. Strong nucleophiles actually prefer SN2, but SN1 can occur with strong nucleophiles. But in this case here, the solvent is dominating the mechanism. All right. So this is polar protic. So I'm going to have to go through an SN1 mechanism. All right. So what happens in the SN1 mechanism first? Anybody help me out?
The leading group has to lead.
That's right. Always a leading group leads. If anything, I think you guys should be able to do that, right? Leading group has to leave. All right. I'm going to generate a what type of intermediate? A carbon cation. All right. Yep, that's right. You can put plus Br minus if you want. I'm typically not interested in the inorganic materials, but that's a byproduct of this is that you will have this compound hanging off. All right, so you see what happens now. So we have to always train ourselves to say, when I draw a carbon cation, I need to check for potential rearrangements. All right, so I'm going to draw this down here because I want to use this again for a teachable moment. All right, so on my right-hand side, I do have a what over here. That's understood. Sorry, not my right-hand side, my left-hand side. I have a what over here? An hydride, right? And on my right-hand side, does that carbon have any hydrides?
Yes.
Check one more time.
No.
How come we don't?
That's
Because
basic.
you got 2 methyl and then 2 carbons, huh?
Yeah, this has 2 methyl groups, 2 carbons, right? Line construction. You should be able to tell the number.
Oh,
right?
okay.
That's all right. 4 lines. So 4 minus 4 gives me 0, right? So there's no hydrogens on that carbon. All right, I'm going to put Amy here. I hope everybody knows that the end of that line is just 1 carbon, and that's known as a what? As a methyl, right? All right, there's no questions with that, right? Okay, good. So let's do both to make sure that we're comfortable with this possibility. So if I do the hydride shift, what do I get out of that? What is going on? Okay. I'm going to move an hydride from that carbon up top, right? I gained 2 electrons, so now my former charge has disappeared there. But now I generate a plus over here. So I went from what type of carbon cation to what type? I started off in the center as what type of carbon cation? Can anybody help me out?
Secondary.
Secondary.
I went from a secondary to a what? from the molecule on the left there.
It's secondary.
Yep, I went from secondary to secondary. Is that productive?
No.
No.
It's not. It's a waste of time. Why would I go from secondary to secondary? Good. So we know that the hydride shift here is unproductive, right? That's the whole take-home point. Doing a hydride shift here will not help. I just go from secondary to secondary. All right. Now we're learning that not only can hydrides move, but also methyl groups. So what happens when I do the methyl shift here? Let's see. Right. Methyl means the methyl group with its 2 electrons, right? I want to make all this gray, actually. Okay, so now I'm going to end up moving my 1 methyl group from that left carbon up top, right? So now that carbon that originally had a plus charge now has a formal minus charge. And this carbon that used to have 2 methyl groups now just has 1 methyl group. I went from a secondary carbon cation to what over here?
Tertiary.
Tertiary. Good. Is that productive?
Yes.
Yeah. This is productive. All right. So this is why a methyl shift occurs in this example, because it allows me the possibility to gain stability from going from a secondary to a tertiary carbon cation. So if I wanted to draw this mechanism out, I would show the methyl shift occurring.
So does it always have to be methyl groups?
Say that one more time.
Does it always have to be 2 methyl groups for you to be able to move one of them?
No, it doesn't. That's a good question. It doesn't. If there's any other group, the methyl group is going to move over anything else. So the ethyl group doesn't really move isopropyl groups, propyl groups, butyl, anything like that. Just the methyl is going to be the group that moves. Okay. Good question.
Are your arrows half-headed or?
No, these are double-headed arrows. These are 2 electron movements. All these are 2 electron movements, double-headed. That's a good
They
question.
just look half-headed. I just couldn't tell.
Yeah. Yeah, I know this is weird. The half one looks like that. And it's just a consequence of ChemDraw. And I'm using ACS settings. So, a little small. I can't make them any bigger without zooming in. But they're double-headed arrows. I have to play around with that setting. I can do that a little bit later. Get to my house. Okay, so I get this rearrangement, and now for my more stable carbon cation, the nucleophile is going to attack, and my final product is going to look like what, you think? Now I'm going to have my methyl group here. All right, I'm going to have my nucleophile here. Do I have to draw a wedge and dash on this molecule? That's a yes, right? Because this carbon is now what?
Chiral.
Chiral, that's right. So I need the wedge version of that, and also I need the dash version. And some people just go ahead and put the dash here as Any questions so far with the?
Wait, can you say again why that's on the dash, why that's on the wedge?
Yep. Every time you attack a carbon cation, you have that possibility to equally attack from the top and the bottom. Because the carbon that gains the extra, because of the carbon that gains the nucleophile generates a chiral carbon. So now you have to show that stereochemistry, right? I get 50-50 mixtures of both of these. But that's a consequence of attacking a carbon cation. Carbon cations are flat. So that means that I can equally attack from the top, which is the wedge, or equally from the back. And I have to show both products here because this carbon is a chiral carbon. Earlier, I didn't have to do that because this carbon was not chiral. There's 2 methyl groups here. Right? Chiral carbons have all 4 different groups. All right, did that answer that question?
Yes.
All right, this is the potential rearrangements and why it went the way it did. All right, let's work on our third type of rearrangement. All right, this is called a ring expansion. Let's take a look at this. All right, I'm going to have the same bromide leaving group. And now I have this compound. All right, what's going to happen here? Again, we're saying that our conditions are favoring. This is not going to work like I wanted to. Control C that. This is SN1 conditions. We established that already. My alkyl halide here is primary, so that was tricky. We said that typically primary alkyl halides do not do SN1. But we said there was a star there only if there's a resonance, or I really should have said a potential rearrangement as well. Okay, so keep that in the back of your mind. So this will undergo an SN1. All right, mechanism. What is the first step here? I think everyone is comfortable with leaving group leaving, right? All right, and it's going to generate a what type of intermediate?
A carbon K9.
Right, carbon cation. Can you guys help me classify this carbon cation? What type of carbon cation is that?
Primary.
Yeah, this is primary. Very good. So there's a couple potential things that can happen. We're going to talk about the most prevalent. Anhydride shift could happen here. All right, so keep that in mind. There's a neighboring carbon that does have a hydride. You could do a hydride shift, all right? However, that's not where we want to focus on right now. We want to focus on something else called the ring expansion, all right? So in this case here, this group breaks, the bond between this carbon and that carbon are going to break to make a new bond. This carbon is going to make a bond there. So this could be a little bit tricky. I'm going to number the carbons a little bit here, kind of work on that. Right. So I'm going to call the carbon of the carbon cation 1. This will be 2, 3, 4, 5, and 6. Okay. All right, so in this step here, the bond between carbons 2 and 6 break. But now carbon 6 bonds with carbon. All right, let's take a look at that really quickly. Let's make this a little bit smaller. That's not what I wanted to happen there. I'll put this in blue. All right, I'm going to translate it first. I'm going to draw it similar to this, and then I'm going to translate it to what you guys should be comfortable with here. All right, so this looks like now this right here, right? I'll keep the same numbers. All right, we said that now carbon 1, smooth out the way. Carbon 1 and 6 now make a new bond. I don't know if that's even going to help. I'm going to keep it like that. Carbon 1 and 6 has a new bond, and carbon 2 and 6 used to have a bond, but it doesn't. So carbon 2 originally had a bond to 3, 1, and 6, but now it only has a bond to 3 and 1. So carbon 2 now has a positive charge. Right? Now, the way that most people would draw this, and hopefully you guys will see this, and this should make sense here shortly, is this is the same thing as saying a 6-member ring. Let's go ahead and copy our numbers back over here. Well, now carbon 2 has gained a plus charge, right? So let's look at the difference here. Why is this productive? Does anybody have a clue of why this would be a productive move here? So I went from something that was primary carbon cation, right? Something that was what?
You lost me.
Okay. This carbon cation is secondary, right? But what is this formation is the fact that a 5-member ring is strained, right? You guys remember that? Ring strain. And the 6-member ring we say has no ring strain. So driving this is the relief of ring strain.
So this is going back to the chair and all that stuff like that?
Yep, you can draw a chair here, but luckily you don't need to focus on that. But this is what governs this ring expansion, is that these rings are going to pop open if it can, because it alleviates ring strain. So I generate a carbon cation next to a 5-member ring. This ring pops open to form a 6-member ring. Now I have a plus charge on carbon 2. My nucleophile is now going to attack. Sorry, these are not the same arrows. Right. And my final product becomes this molecule that has a nucleophile attached. Do I need to draw a wedge and a dashes for this molecule? That's a no, right? Because that carbon there is not chiral again. All right, I know somebody said they were lost. I just wanted to get through all this and just talk about it one more time. Okay, let's look at this again. So a ring expansion, and I should have gave the details up here, I'm sorry, is that I'm going to relieve ring strand by generating stable, I should say more stable, carbon cation. I got one more to go, but I'm almost there. I think we're going to make it here. Bring it down a little bit here. All right, so ring expansion is going to relieve ring strain by generating a more stable carbon cation. So when this Lehman group leaves, I generate a primary carbon cation, right? This primary carbon cation has next to it a relatively strained ring here, which is a 5-member ring. This ring will open to generate a 6-member ring, all right? This 6-member ring is a better ring, and it has a secondary carbon cation. So there's favorable things going for it. Now the nucleophile will attack, and you would generate this as your final product. Okay? You guys feel better with that?
Dr. Cooper,
Go ahead. Yes, ma'am.
real quick, just for the sake of my notes, what exactly caused the bond between 2 and 6 to break?
Yeah, because it's next door to a carbon cation. You could have used 2 to 3 or 2 to 6. It doesn't matter. Just one of these two bonds near the carbon cation. Just out of convenience, I used the bottom bond here. So if you look at 2, any bond between 2 will work. So 2 and 3 bond is okay, or 2 to 6 bond. Those are the only ones that will open productively next to the carbon cation to expand the ring to something bigger. Right? Did that answer your question?
Yes, sir.
Okay, great. I should have used something. I should have used a 4-member ring here. Sorry, that would have been probably a better example. But it's good that you saw this one. So any strain ring here will work. All right. So that means being next to a 4-member ring or being next to a 3-member ring will always pop open. If I'm next to a 6, will that pop open? No way, right? I'm not going to a 6 to a 7 because the 6-member ring is so much more stable. All right, so I should mention this over here. This has to be a carbon cation next to a 3, 4, or 5-member ring only. Okay. All right, any questions so far with a ring expansion? Okay, good. Let's do the last one. The last one is probably the easiest of the two. And this is just resonance, right? So what happens with resonance? Pi bonds can be localized. The carbon cation generate more stable. Let's take a look at an example here really quickly. I'm going to use the same nucleophile and solvent for this as well. All right, let's say that I start off with this structure here. Everyone hopefully is comfortable with the fact that this mechanism type again would be SN1. The solvent is dominating this polar aprotic. So what happens in my first step here? What will you guys tell me? The leaving group's going to leave, right?
Yes, sir.
All right. And I'm going to generate a very reactive intermediate known as a what here?
Carbon K9.
Right, carbon cation. So all I need to do now, I need to check, could this rearrange, right? There is a potential hydride shift that can happen, but it will take me from something that's secondary to primary. You want to convince yourself that doing a hydride shift here will not work. Right? So what could happen? Next door, I have a what?
A double bond.
That's a double bond. There is a hydride here. Keep in mind, you cannot do a hydride from a carbon involved in a double bond. All right, this bond to H becomes a little bit stronger. All right, so that cannot move. So instead, however, we know that pi electrons are very easily delocalized. Right? And so I'm just gonna move 2 electrons over. So these 2 electrons are gonna move over. Let's see if I can get a better looking arrow for that. So in doing so, I go from a secondary carbon cation to what you think?
A tertiary.
Jay.
That's right. You guys are right on it. So now this double bond moves here and I generate that carbon cation. So I made a mistake here. This is secondary, but also what? All right, this is a secondary allylic carbon cation. And over here on the right, this is what type?
Benzylic.
Oh, this is tertiary allylic.
Oh,
I need that phenyl ring to be benzylic.
Dr. Cooper, can you? Oh, you say you had. I need a ring to be benzylic.
Yeah, you need a phenyl ring, right? You need this
Oh.
ring.
Okay.
Here is that carbon is benzylic. Right? So I'm actually gonna. I'm glad you mentioned that. I'm gonna go ahead and put this up here. Actually, I'd like to put it bigger. All right, this is a benzylic carbon cation. I'm going to try to put the arrow at the carbon I'm indicating. Is that carbon? Oh, that's the wrong one. That carbon right there. All right. And don't forget that this I thought I clicked on that. This carbon cation here is known as what type?
Your screen is kind of glitching out. So what did you say?
I was saying that this second structure I just drew over here This is known as a allylic. Right. I'm sorry that my computer is messing up. I think the school is probably trying to tell me a message. I hit it up. I'm almost finished. Okay, and this, can you guys still see my screen? Yes or no?
Yes.
Okay. This second structure is known as an allylic when I'm one away from a double bond. All right, so you want to keep these two carbon cation types in your mind. All right, these are the two that have heavy resonance potentials. All right, the allylic carbon cation or the benzylic. In this case here, I have an allylic. So I'll go from a secondary allylic carbon cation through resonance delocalization to a tertiary allylic. Then what happens in my last step?
Dr. Cooper,
Okay, go ahead.
I don't know if it's just me, but when you turn your colors to that grayish on that white background, I can't see that.
All right, I'll just change the background. Yeah, there you go. Something lighter. Okay, that's not going to work. I'll just go black for now. I'm trying to choose a color that didn't take away from the main examples, but I can do that a different way. One sec. I'll just make it smaller. Okay, does that help now? Between the benzylic and the allylic system. When the nucleophile comes in, now my final product is going to be where the nucleophile attacks here. And this is going to be my final product. Do I have to draw a wedge and a dash for this molecule? Hopefully everyone says no, because the carbon of the nucleophile or the carbon that has the nucleophile is achiral. So that means that I do not have to draw any wedges or dashes. Okay, any questions with this last potential rearrangement?
A question of I got a question about the ring expansion one. You
Okay.
said that we can possibly do hydride shift.
Yeah, a hydride shift could work for that one.
So would you take off points if we would have did either or?
No, good question. Typically when I design a question like this, I'll be ensuring that there's only one major rearrangement type that should occur.
Okay.
Very good question. Just because I'm doing this off the top of my brain, this is the example that I thought of. But when I saw it, there's immediately I saw that I drew a hydride here. The way I could change the question, just put a methyl or something, not even a methyl, I'd put like a phenyl group here. And then you guys know that there's no hydride or any methyl groups that can move over. So you only can do the rearrangement type. I'm sorry, the ring expansion type.
Okay.
Good question. Very good question. All right. Any other questions? Okay, good. No questions for now. I do have office hours. Don't forget, I got office hours. Well, boy, actually, tomorrow's going to be a weird day. I'm giving a talk tomorrow, so my office hours will be available After that talk, I think it'll be around 11:30. I should be back to normal. So if you do want to talk over things, shoot me an email and we can schedule for any time from 11:30 to about 1 o'clock ish. All right, I do have a 2 o'clock lab. All right. Fridays, I typically don't have any office hours, but I do have a small window before 2 o'clock. So right after class, before 2 o'clock, and anyone has any other questions, please stop by. All right. There should have been a set of notes on SN1 and SN2 on reactions that I sent you guys, and there should have been a list of practice problems. I would highly recommend trying those problems, and if you need to, schedule some time during office hours, and we can talk about those problems. Right? I'm going to try to release the answer key to all of the potential problem sets I sent the night before the exam. That's typically how I like to do it. I know things are different now with the online stuff, but try to use office hours to do that. My number one teaching strategy, I guess, that I really feel like it helps is that providing answers too early sets students up for failure with the sense that you guys use memorization, right? Which is a great skill, but it doesn't help as much with organic. There's something about trying a problem and thinking about it and thinking about all the different possibilities that you start to train your brain to think at the level to be ready for a test, right? And I don't want to take away that opportunity. So those problems are designed for you to take some time to sit and think, right? Even if you can only do 1 or 2 problems, that's good. Trying 1 or 2 problems with what you know now is better than just trying to look at the answers and memorize what I did and think that you'll be ready to do that on the test, right? Don't fool yourself there. It's not going to work the way you think. It helps. I'm not going to say it doesn't help, all right? But it's not the same as actually mentally training your brain. Once you do it and you know how you did it, you have a greater tendency to remember doing it that way when it comes to a test. Okay, good. I'm going to stop the recording. I'm going to stop the screen share too. I'll give these notes to you guys shortly. And I'll take any questions here